In this video, I want to discuss the Degree-Genus Formula, which is a really nice formula relating the degree of some algebraic curve to its genus considered as a real surface. So what do I mean by this? Let's consider we have some equation like y squared is equal to x cubed minus x. So over the real numbers, this will look like some curve like this, and then you'll have another component over here. But then if you consider the picture of the complex numbers, then what will happen is that the solutions to this equation will locally look like C, similar to how this guy locally looks like R. In other words, it will be some sort of a surface instead of some sort of a curve. And we can ask, well, if this is a surface, and it turns out that the surface is orientable, basically because C, any two maps holomorphic maps between C or orientation preserving. So we can ask, this is an oriented curve, or an oriented surface, I should say. So what's the genus of that surface? And there is a very close relation between the degree of the polynomial used to define some equation and the genus of the surface that it cuts out in C2, or more precisely, projective space. Okay, so here's the theorem. For a non-singular degree D curve in CP2, the genus of the curve C is equal to D minus 1 times D minus 2 over 2. Or, I mean, I guess maybe you want to write it as D minus 1, choose 2 or something like that. But basically what this says is that if you, what is a degree D curve, by the way? It's just something defined by some homogeneous polynomial f of x, y, z is equal to like x to the d plus y to the d minus 2 x squared plus z cubed y to the d minus 3. So all the homogeneous terms have degree D, and you set that equal to 0. Or in other words, if you want to look in the affine picture, then it just says that it's defined by some polynomial like y squared minus x cubed plus x equals 0, where the maximum degree of any term is equal to D. Okay, so how can we prove this statement, saying that this degree closely relates to the genus of the curve? There's two methods of proof, which I want to show it here. The first one requires something called the Riemann-Hurwitz formula, and the second one will use some fancy tricks involving line bundles. Okay, so yeah, let's first see how we can see that the solutions to the equation x squared plus y squared equals 1 in CP2, so in complex space, or really complex projective space, looks like a sphere. Looks like S2. So how can we see this? Let's draw the picture over R. So x squared plus y squared looks like this. And what we can do is we can fix some point, like this point, -1, 0. And what we can do is we can draw lines emanating from this point and intersecting the circle at different points. And what we notice is that each one of these lines intersects the circle at exactly one other point. And the reason for that is that any line will intersect a conic section at 2 points, generically, unless it's tangent. And since we already know one of the points of intersection, we know that it must intersect the circle at one other point. Now there's one line which is tangent to the circle, which is this vertical line over here. But we consider this sort of second point of intersection to also be -1, 0. So this does is it sets up a one-to-one correspondence between points on the circle x squared plus y squared equals 1 and the set of slopes, which in this picture is RP1, but if we look at the picture over C, then this will be inside CP1. And the space of slopes is essentially the space of lines through a single point. This will be inside CP2. And so the space of slopes will be in one-to-one bijection with CP1, which locally, or not locally, but which looks like the sphere. So you can see from this argument that the circle or in fact any conic, you can do the same sort of argument over a complex projective space will look like a sphere. So what we can do instead is, instead of picking a point on the circle, we can pick a point that is not on the circle and still draw rays emanating from this point and see how it intersects the circle. So we can see that now every slope m will correspond to not one but 2 points. And there are some points on the sphere where it only corresponds to 1 point. And this is if it's tangent. So we see that at most points it corresponds to, at most places it corresponds to 2 points, but at some places it'll just correspond to a single point. And so what we have then is we have a 2-to-1 mapping from the solutions to x squared plus y squared equals 1 to CP1, which is the set of all slopes. And this is kind of a lie because it's not exactly 2-to-1. It's 2-to-1 except for these points. So this being exactly a 2-to-1 mapping, we call this a degree to branched cover. So that means at most points, there's 2 points which map to us. If we look at the preimage of a single point here on the sphere, then usually there's 2 preimages which correspond to the 2 points of intersection over here. But at some points on the sphere, maybe this is one of the slopes, there will only be 1 preimage. And sort of this preimage should count for 2 points because if you look at a nearby point like over here, then it'll intersect at these 2 points, which sort of come together to the single point over here. So what we say is that this point over here ramifies to degree 2 in this mapping from, in this 2-to-1 mapping from these solutions to the solutions. And there's a formula called the Riemann-Hurwitz formula, which allows us to have a handle on how the Euler characteristic of a map between 2 surfaces. So let's say that we have a map from this guy to a sphere, which is maybe branched at a few points. So one example of such a map is you can take the genus 2 surface and sort of flip it by 180 degrees and then quotient out by that action, then you convince yourself that that's a branched covering of the sphere. And the Riemann-Hurwitz formula says that if we know the branch points and we know the degrees of ramifications, by the way, these are the branch points, which are the points where you have fewer than the expected number of preimages, then we can actually relate the genus, or more precisely the Euler characteristic of the 2 surfaces. So I'll maybe make another video about this formula, but I'll just state the theorem right here so I can use it. So let's say that we have a map between 2 surfaces, or I guess maybe instead of C1 and C2, I'll say S1 and S2. Then the formula says that chi, and this is a degree D branched cover. Then what we have is that chi of S1 is equal to D times chi of S2 minus the sum over all ramified points of the degree of ramification minus 1. So as an example over here, you can check that there should be, I think, just 2 ramified points. Yeah, so there should be 2 ramified points over here which correspond to this point and this point, and there are no ramified points over the complex numbers. So what we can do is we can plug this into the formula, and we can see that chi of S1, which is the space of solutions to x squared plus y squared equals 1, which is 2, is equal to 2 times chi of S2, which is the CP1, which is also 2, because 2 is the Euler characteristic of the sphere. And recall that the Euler characteristic of a genus G surface S is equal to 2 minus 2G. And then here we have 2 points of ramification, and each one ramifies to degree 2, which means that we expect to have 2 preimages, but we only have 1 preimage. And so here we're taking minus 1 plus 1. And indeed, this checks out that we can sort of equate these two guys since we know all this information. But the nice thing is that if we did know the Euler characteristic, in other words, if we did know the genus of our initial surface, then if we knew the degree of the map, we knew the degree of the resulting thing, which is CP1, and we knew all of the ramification points, then we could figure out what the Euler characteristic of the initial thing was. So we can employ this trick by doing the same thing for something like this, where we choose some arbitrary point away from our curve, and then we take lines which pass through this point and see how many times it intersects our curves. And then in general, because a line will intersect a degree d curve at d many points over the complex numbers, you can check that. That essentially corresponds to the fundamental theorem of algebra. There will be a degree d branch cover, and we can analyze which points are ramified. In other words, that corresponds to like which at which points is the line through this point tangent to our curve, and by analyzing that, we can hope to figure out the genus of the surface. So we'll look at a special example, which will be the projective curve defined by x to the d plus y to the d plus c to the d is equal to 0. And this is sometimes, I think, called the Fermat hypersurface or curve or whatever. And what we can do is we can try and figure out what the genus of this would be. And this is the set of solutions to this is lying inside CP2. Okay, so how can we do that? Well, the set of solutions to this will be some set of homogeneous coordinates, x, y, z. And what we can do is we can find a mapping from this set down to CP1 by just keeping track of the x and y coordinates. And so first off, I want to make sure that this map is well defined. Remember that that if you're mapping to CP1, both of these coordinates can't be 0. But if x and y is equal to 0 and we satisfy this equation, that means z was also equal to 0, which is not a valid point in CP2. So this map is well defined. And to sort of see what this map is doing, what we can do is we can restrict to the affine picture. Let's look at x to the d plus y to the d plus 1 is equal to 0. And in this sense, we're mapping down to x colon y and projective coordinates. But then this is really the same as 1 y over x. And if we sort of, I don't actually know what the graph will look like, but maybe like this is the graph of our curve, and then maybe this is the plane. Then when we're keeping track of the value y over x over here, what we're essentially doing is keeping track of the slope of the line that connects it to the point through 0, 0. So it's the same exact thing that we were doing earlier. And now we can see what the degree of what the degree and branch points of this map are, and then figure out what the genus of this curve is. Okay, so how can we do that? Well, we can see that over here, if we pick two values, say x0, y0, in CP1, and we look at its pre-image, then that will be all the points x0, y0, z, such that x0 to the d plus y0 to the d is equal, plus z to the d is equal to 0. And if, say, this guy is some constant c, then this is saying that z to the d is equal to, or I guess minus c, then z to the d is equal to c. And so, in general, this will have d different points, or different values for z, because you can take any of the dth roots of c, which differ by roots of unity. However, if c is equal to 0, then that implies that z is equal to 0, which implies that we only have 1 point. And so what that means is that whenever c is equal to 0, we have only 1 point, which means it's fewer than the expected number of points, which is d, and so we have a ramification point. And this point ramifies to degree d. And the reason for that is because we expect d many points, but we only have 1 point, so it ramifies to degree d. And so what are the times when c is equal to 0? Well, this corresponds to when x to the d plus y to the d is equal to 0. And in projective coordinates, these will just be the points 1, zeta to the k, or maybe zeta d to the k, where zeta d is some fixed primitive dth root of unity, and projectively, these are the only points at which x to the d plus y to the d is equal to 0. And we can see that because there are dth roots of unity, that there are d many points. which verify like this. And so now let's call this guy S, and we can see that chi of S is equal to d chi of S2, which is the sphere, minus the sum over d many points, the degree of ramification minus 1, which is d minus 1. And so if we plug this in, we get 2 minus 2g is equal to 2d minus d squared plus d. And then if we rearrange this, then we get that g is equal to d squared minus 3d plus 2 over 2, which is equal to d minus 1 times d minus 2 over 2. Okay, cool. So we've just shown that for this special case of the Fermat hypersurface, that indeed the degree-genus formula holds. However, it turns out that this special example can actually be generalized into any example. And so what that means is that our special calculation that we've done just basically implies the rest of them. And how's the argument for this? Let's say that we have, let's say that f of x, y, z is our Fermat cubic curve, or Fermat degree d curve, which is x to d plus y to d plus z to the d is equal to 0. And then let's say that we have some other polynomial g of x, y, z, which is also some degree d polynomial, homogeneous polynomial. So the equation g is equal to 0 defines some hypersurface. So what we can do is we can sort of interpolate between these two. And what that means is that we can take f times 1 minus t plus g times t is equal to 0. And so I guess maybe I should write the other way. 1 minus t times f plus t times g is equal to 0. And so at t is equal to 0, we get the equation f equals 0. In other words, the Fermat hypersurface. And at t equals 1, we get the equation g is equal to 0. In other words, the solution to the degree d polynomial that we want. And I'm going to assume that this is non-singular. And you can check that this one is also non-singular. So then what you can do is you can argue that because we can interpolate between these two, then the solutions must look topologically the same. And the argument goes as follows. So suppose you want to interpolate like from this cubic curve to like this cubic curve. Then maybe in the intermediate, what would happen is you get something singular, which looks like this. And it turns out that singularities could change the topology of what you're looking at. Like, even though this is just over the real picture, we can see that or maybe this one would be the singularity, maybe the singularity would be actually this one. But if we pass through a singularity, then we might end up changing the topology of our space. However, it turns out that if we can interpolate between two curves and have no singularities, then the curves will look the same. And the reason for that is, let's say that we have some curve over here and some other unknown curve over here, but we have some interpolation between them such that none of the fibers are singular. So all of them are continuous. So we can interpret this as like a map from this three-dimensional shape, which is like a total interpolation between two surfaces, to 0, 1. And what we can see is that, let's say that we pick some non-singular point over here where the preimage is non-singular. Then for any small neighborhood of this, if we sort of perturb this curve a little bit, then that should not topologically change anything. In other words, if being non-singular is an open condition, so if we perturb this a little bit, then it won't add any singularities. And if it doesn't add any singularities, you can sort of convince yourself, I don't know, I mean, intuitively it makes sense that nothing should change topologically. And the rigorous argument for this would be to use something like the implicit function theorem or the inverse function theorem, or one of those theorems, to say that if this function does not have zero derivative anywhere, then the fibers will all look the same. And so sort of interpolating this argument from the beginning to the end, what you see is that the initial curve and the final curve need to look the same. So I just said that we can take an arbitrary like interpolation here between f and g, and essentially for each value t, like this is t equals 0, this is t equals 1, for each value of t we get another curve. But similar to like this picture, we don't guarantee that we can skip singularities. However, there's a nice sort of thing, which is that we can take t to lie in C rather than just in R. And then what happens is that the number of points, let's call this, I guess, h of t. And so h of t is some, for each value of t is some homogeneous polynomial in x, y, and z. But the places where h prime of t is equal to 0, which means that there exists some x, y, z, such that h of t x, y, z is equal to 0. The number of points at which this is true will be codimension 1 over the complex numbers. In other words, it will be just a discrete set of points. And so even if like we want to get from 0 to 1, and let's say that these points that I've highlighted are points at which there's some singularity in the curve h of t, we can sort of avoid these singular points by choosing some curve in C which avoids them. And because the set of points at which it's singular is codimension 1 in C, we can always just choose a path that avoids a discrete set of points. And so we can choose some interpolation which avoids any singularities, and thus the initial topology and final topology must look the same. And if you don't like that argument, there's another way to sort of proceed, which is to say that, let's say that we look at the space of all degree D polynomials. And all degree D polynomials are essentially specified by coefficients. So that'd be like, I don't know, some coefficient a x to the d plus b y to the d plus c x y to the d minus 1, and so on and so forth. So you just have a bunch of is equal to 0. And so you have just a bunch of coordinates, a, b, c, and so on. And if you scale the equation by some constant, then that doesn't really change the surface which it cuts out. And so really you should consider these up to scaling. In other words, consider them as projective coordinates. And then the set of all these, in other words, the set of all degree D surfaces is going to be some p to the big N. And what you can do is you can sort of look at, okay, what are the, you can take a function from Pn to z, which says, okay, let's take a point in Pn, look at the curve which it corresponds to, and look at the genus of that resulting curve, or resulting surface. And the thing is, if you have a singular curve, then it won't have a genus. So you want to sort of exclude all singular curves. So you want to consider Pn minus the set of all singular curves. But this is defined by the vanishing of some discriminant, because essentially a curve is singular if there exists some x, y, z such that f of x, y, z is equal to f prime of x, y, z, or I guess the derivative with respect to z, x, and y is equal to 0. Okay, so the set of the singular curves will correspond to something which is codimension at least 1 in Pn. And because it's codimension 1 over the complex numbers, that means it's codimension 2 over the real numbers, and so you're moving something which is at least codimension 2 as a real manifold, or as a real subspace. And so what that means is that this space is connected. And so we have a map from some connected space to Z, which is the genus. And because the space is connected, then it can only take on one value because Z is discrete. And so we know that from a hypersurface, which you can verify is non-singular, it takes the value determined by the degree-genus formula, and so this must hold for every single hypersurface of degree d. Okay, there's another really slick argument of this, which goes through some arguments with line bundles, and here is the argument. So let's say that we have like our four-dimensional C2, and within here we have our hypersurface. So at every point, what we can do is we can take the tangent plane, and we can also take the normal plane. So we can take TP, let's call the surface S. So we can take TPS, and we can take also the normal plane to the surface S. And what this does is it sort of decomposes the tangent space at P of C2 into two components, the tangent component and the normal component. Now the thing is, the normal component isn't really, the normal component, by the way, is all vectors which are like orthogonal to the tangent plane, but this isn't really well defined in general because in general, we want to just work over the complex numbers. You don't want to impose any metric on these things. So really what we should define is the normal space at S is defined as the vector space, which is the tangent space of the ambient space, which is C2, or I should really say CP2, quotiented by the subspace, which is the tangent space to your surface. And what this does is this defines some vector bundles, which is TS, TCP2 restricted to S, and the normal bundle to S. So this one is a rank 1 bundle. Similarly, the normal bundle is also rank 1. And because they look like one-dimensional vector spaces, and this one is rank 2. Yeah. And these are related by an exact sequence, which is that the normal bundle of S is the quotient of the tangent bundle of CP2 by the tangent bundle of your curve. And it turns out that if we have such an exact sequence, then what we can do is we can analyze the Chern class of these, and it turns out to give our formula. And the reason is that the Chern class of the tangent bundle to the surface is related to the genus, and the tangent bundle to the normal of the surface is related to sort of like if you were to deform the surface a little bit in CP2, how many times would it intersect itself, and that is related to the degree of the surface, because essentially it's like Bézou's theorem. So how can we use this fact? Well, this turns out to imply that the maximum wedge product of TCP2 is equal to the maximum wedge product of tangent bundle times the maximum wedge product of the normal bundle. And this is true in general, that the tangent bundle, that if you take the maximum wedge product of the outside things, then it's equal to the maximum wedge product of the middle thing. It's a non-trivial fact, but it turns out to be true. And these guys, I guess I should say restricted S, and these guys form line bundles on S. And so what we can do is we can analyze the Chern classes of each of these, and we have that the first Chern class, I guess I'll call this guy K restricted to S. The Chern class of K restricted to S is then equal to the Chern class of, well, the first wedge power of a line bundle is just itself, so that's TS, plus the first Chern class of the normal bundle. And so the first Chern class is just, the line bundle is just to say that if you take a generic section of the line bundle, which is meromorphic, then how many zeros does it have minus how many poles does it have? So it's the degree of the vanishing, it's the degree of some generic section. And one way to interpret this is like if you have some curve and you have some normal bundle on it, then a section on it will essentially give you an infinitesimal deformation of the curve, and then the points at which the section vanishes correspond to the points of intersection of the curve with the infinitesimal deformation. So what we can see is that the first Chern class of the normal bundle corresponds to the intersection of S intersect S tilde, where S tilde is a slightly deformed um, another copy of a degree D surface. And so because both of these guys are degree D, we see that the first Chern class of the normal bundle of S is equal to D squared. Okay, the Chern class of the tangent bundle is equal to the Euler characteristic of S. And so this is related to, you can think of it in the real analytic case as like the Poincare-Hopf theorem. Or in algebraic geometry, you can directly show that the Chern class of the cotangent bundle is negative the Euler characteristic, and you can use some Riemann-Hurwitz argument for that to find an explicit one form by looking at a map from your surface to S2. But just take this if you don't believe me. And then we can compute this guy. And so the thing is that K of CP2 is the line bundle O of minus 3. And what this means is that a generic section of this in CP2 will have three different, sorry, I should say this should be K dual. So it'll have three different poles. So what is K? K is lambda 2 of the cotangent space to CP2. And the cotangent space, you can interpret this as like essentially two forms on CP2. And so you can choose some local trivialization and choose some two form which looks like dx over x, wedge dy over y. And then you'll see that this has two poles, one on the plane x equals 0 and y equals 0. But it might also have a pole along the plane z equals 0. So if you do a change of coordinates, so this is the change of coordinates where, say, z is equal to 1. If you make a change of coordinates to where x equals 1, then you'll see that this transforms into dy over y, wedge dz over z, maybe plus or minus. So it also has a pole at z equals 0. And so we see that this has three poles, and so this is equal to O of minus 3, which then implies that K dual is equal to O of 3, which means that a generic section of this line bundle will have a zero locus, which is a degree 3 curve in CP2. Okay, so now we want to look at the degree restricted of this guy restricted to the surface S, which we can interpret as the intersection of this degree 3 curve with the degree, if we take a generic section of this guy in CP2, then that'll be some homogeneous polynomial f of x, y, z of degree 3. And in order to figure out the degree of O of 3 restricted to S, what we can do is we can look at the zero locus of f of x, y, z, intersect the zero locus of x, S, which will be just f is equal to 0, intersect S, and because this is a degree 3 and this is a degree D, by Bézout's theorem, this will be 3D. And so we see that this is now equal to 3D. Cool, so now we have 3D is equal to 2 minus 2g plus d squared, or again, g is equal to d squared minus 3d minus plus 2 over 2, which is equal to d minus 1 times d minus 2 over 2, which is another sort of way to approach this formula, which is, I guess, a bit more abstract and less analytic. But the nice thing about this one is that once you develop the notions of tangent bundles and normal bundles and line bundles and all of this over different fields, then you can actually generalize this to saying something about curves over finite characteristic. And yeah, that's everything. Okay, so there's actually another really nice argument to sort of see the count relating the genus and degree. And while it's more elementary than the other two methods, it's a bit more sus as to why it actually says anything about non-singular curves, because we're actually going to use very singular curves to get this count. And so the reason that we focused on non-singular curves until now was because if you had something like a singular curve, then you would end up with something like this, like a singular torus. And well, is the genus of this 1 because you can sort of like connect these two edges, or is the genus 0 because you can sort of split it off and make it into a sphere? and that's unclear. But somehow we can actually use singular curves to get a genus count. And so what I'll do is I'll actually consider like a maximally degenerate degree D equation. And so that'll look like the union of a bunch of lines. So this is an example of a degenerate degree 3 equation, which is maybe something like x minus y, x plus y plus 10 times x minus 3 is equal to 0. And so this is what the picture looks like over R2. But if you look at the picture over CP2, then what we'll have is that each line corresponds to a sphere. And every pair of lines over here needs to intersect. And each of those points of intersection will correspond to a point of tangency between two spheres. So what you'll end up with is three spheres which are mutually tangent to each other. And we can see that there is a hole over here in the middle of the three spheres. And that sort of makes the three spheres look like a torus, except the torus has like these um, three circles which are pinched down to make these three regions into spheres. And if we had four lines, then what we'd have is these three circles as before, and then we'd have a fourth circle on top of them. And then you can sort of see that there's four holes in the shape of a tetrahedron in this configuration of spheres. And this corresponds to a genus 3 surface. And this is the case for like four lines. And this agrees with the count d minus 1 over 2 because 3 choose 2 is 3. And if you aren't convinced that this thing has three holes instead of four, then you can think of it as like this. If you smooth out the vertices like we sort of smooth this out to make a torus, then this kind of looks like something like a t-shirt, and you can convince yourself the t-shirt is genus 3. Okay, so in general, what will you have? Well, you have a union of spheres, and these spheres are really lines in CP2, and each of these spheres will be pairwise tangent. Pairwise tangent. And this is because any two lines intersect. And so what this means is that we can sort of try and see what a non-singular curve looks like by trying to analyze these. And the reason we can do that is you can sort of play around this with on Desmos. If you replace this 0 with a small little value epsilon, then you'll see that this degenerate union of lines will actually change into a smooth like degree D curve. And so you can try and convince yourself that if you were to deform any of these a little bit algebraically, then these sort of nodes will resolve themselves into something smooth. And so we can try and understand the genus by trying and understanding this picture. And one way to understand this picture is by drawing one vertex for each sphere and drawing one edge for each point of tangency. So we have one of these vertices for each of the spheres, and each point of tangency corresponds to one of these edges. And this corresponds to the three sphere picture, and we can see that there's one hole corresponding to the one hole over here. And if we had a fourth sphere, then we'd add a fourth vertex and have one line joining each of these vertices to this fourth vertex. And we can see that we have three holes, which corresponds to the fact that this is a genus 3 surface. So in this alternate picture, what we have is a D vertex graph, which is complete because every two vertices has an edge joining them. And this corresponds to the fact that any two lines will have a point of intersection, or in other words, any two spheres in CP2 will be tangent to one another. And then we can try and analyze the number of holes in this graph. Or in other words, we want to compute the genus of this graph G. And what we can do to do that is we can look at the Euler characteristic of G, which is equal to the number of vertices minus the number of edges. And the number of vertices is D, and the number of edges, because every 2 points is paired up, is D choose 2. And at the same time, the Euler characteristic is 1 minus G, which you can think of as like the number of connected components minus the number of holes of the graph. And what we get from this is that G is equal to D choose 2 minus D minus 1, which is equal to D minus 1 choose 2, which you can either do at the algebra or note that this is D minus 1 choose 1, and then use that like Pascal's triangle formula. Now, I don't know of a direct argument to like combinatorially get D minus 1 choose 2, but and even though this guy corresponds to the singular curves, hopefully this should give you at least some more intuition as to why this relationship should hold. So one thing that really confused me at first was, let's compare some values of d and g. So if d is equal to 1, then g is equal to 0. And that corresponds to the fact that a line in CP2 is just a sphere, or CP1. If degree is 2, then g is still equal to 0. And that corresponds to the fact that a degree 2 equation will also cut out a sphere, except now it's sort of like a doubly wrapped sphere. If d is equal to 3, then g is equal to 1, and this corresponds to the fact that any non-singular degree 3 equation will give you a torus. If d is equal to 4, then g is equal to 3 now. While d is equal to 5, then g is equal to 6. So you may ask, what happened to genus 2? And what happened to genus 4 and 5? And so one thing which makes this confusing is that this essentially is a complex manifold, it's essentially a real surface, but instead of considering it as a real two-dimensional manifold, you consider it as a one-dimensional complex manifold. And you can put a complex structure or a complex manifold structure on any orientable surface. So like, in what dimension should a genus 2 surface live? And it turns out that because of this argument, you can't embed a genus 2 surface into CP2, you actually need to embed it into CP3. And conversely, it turns out that any surface can be embedded into CP3, but like the ones which don't appear in this table can't embed into CP2. And maybe the last point about this argument is like, how do you actually deduce information about non-singular curves from singular curves? And this requires some level of machinery. I think you can show something like along some smoothly varying family of curves, the Euler characteristic doesn't change, and there's a way to define the Euler characteristic in algebraic geometry for singular curves, and you can sort of use that to show that the genus does not change either.